Hey everybody, my name's Ryan Schmidt. I'm a developer on the Direct3D team here at Microsoft, and today I'm going to talk to you about conservative rasterization. And really the issue is that we've got 16.8 fixed point precision in the rasterizer and discrete sampling there. Like if we're just sampling the center of a pixel, we might miss a contribution from a primitive that only partially covers that pixel. And so the solution is to be conservative with the geometry and the coverage and make sure that we compensate for some of the shortcomings in the rasterizer in that it can't fully represent the floating point vertex coordinates that you might be feeding to the graphics pipeline. And so in general, the idea is that we want to render all pixels that at least partially cover a primitive. And there's some terms that go along with this. There's overestimated or outer conservative, and that's if we've got a primitive that's being extra conservative about what pixels that primitive might light up. And there's also underestimated or inner conservative, and that's sort of the opposite, where if we have a pixel that's on the inside of a triangle, it's guaranteed to be fully covered. Another term is the uncertainty region, and that's basically what I've been diagramming here. That's the outer uncertainty region. This is the inner uncertainty region. And lastly, we've got degenerate triangles, and those are typically not rasterized because they're zero area triangles that may not have been degenerate in floating point, but due to the 16.8 fixed point precision in the rasterizer, become degenerate once they're snapped. And we kind of lose those, and typically that's not relevant for generating an end image or something like that. But for conservative rasterization, it's important for some use cases that we don't lose those degenerate triangles. And so we've got three different tiers of conservative rasterization, and each one enables a new class of use cases. So for tier one, we've actually got started off with a half pixel uncertainty region. And so what that means is if we've got our triangle, it can be thought of as sort of a swept, like the uncertainty region can be thought of as a swept square around the edge of the primitive. And so it's as if we had a square that's, didn't draw that super well, but imagine it's centered on the primitive edge there, and it's actually fully 1 pixel wide. And the uncertainty region that's going to extend out this way is half a pixel, if that makes sense. So you can imagine this thing is essentially sweeping around this primitive to produce our uncertainty region. And then that means that if this uncertainty region intersects any pixel, that this one will get rasterized. Whereas before, we might not have a sample point there, or the primitive has been snapped and actually isn't intersecting that pixel, and so it wouldn't get rasterized. And so the use cases for tier one are stuff that don't rely on degenerates, and don't care if those get cold, or the inner conservative coverage that we were talking about, the underestimated conservative rasterization. And this is useful for binning for child rendering or something like that. So next we'll talk about tier two. In this one, we reduce the uncertainty region, and so we have less false positives. And so with the 1,256, again, you can think of our swept square going around. So half of that square is the 256 of a pixel. And the other thing that tier two gets you is that degenerates are not culled. So tier one, we've got degenerate culling. You'll lose those triangles if when they get snapped to the 16.8 fixed point precision in the rasterizer, they're degenerate. And there's some interesting things there. They're all going to be back facing. And so you can cull them with is front face in HLSL if you need to. Like an app can actually make that decision itself. And then the other interesting thing is that you'll get V0 attribute values for any interpolated value, because you can't interpolate zero area triangles with barycentrics. So those are some of the interesting points about degenerates. The use cases for this is where losing a primitive is unacceptable. And so conservative rasterization can be helpful in generating spatial data structures using the GPU for consumption on the CPU, something, for like CPU collision detection or something, you might want to bin all of your primitives. And in some cases, losing a triangle that happened to be degenerate the way you were setting up your viewport and transformations and stuff like that, that would be unacceptable. And so tier 2 gets you that. Lastly, we have tier 3, where we've tightened the uncertainty region even more to 1/5/12th of a pixel, which is actually the mathematical minimum based on the 16.8 fixed point precision in the rasterizer. And so that gives you the least amount of false positives, and so you'll be rasterizing less pixels, or the least amount of pixels, and still being conservative. It also adds SV inner coverage, which is a system-generated value in HLSL, or system value in HLSL, that will tell you whether a pixel is guaranteed to be fully covered. And so what that says is conservatively, for any snapping error that could happen in the rasterizer, this pixel will be fully covered. There'll be no partial coverage that you have to worry about. And so some use cases that enables is occlusion culling, because then you can say, this wall or whatever definitely covers this pixel. I don't have to worry about, rendering anything behind there. And other things it's useful for is like analytical anti-aliasing, things like that, where you could optimize your algorithm and just sort of shortcut pixels that are fully covered. And so tier 3, while it's got the smallest uncertainty region and adds SV inner coverage, it still has everything that the other tiers have. Specifically the degenerate culling from tier 2. And so tier 3 sort of has all the features, and that's where we want to end up with everybody supporting tier 3. That's not the case right now. And so the other tiers, if you don't need the features added from some of the subsequent tiers like tier 3, and you target a lower tier, that'll actually help you hit more hardware, because any tier 3 hardware can do a tier 1 algorithm. So that's a good way to make sure that you're targeting the most amount of hardware for your algorithm, instead of limiting yourself to only tier 3 hardware when you don't actually need all the tier 3 stuff. Anyway, thanks. This has been a presentation on conservative rasterization. I'm Ryan Schmidt from the D3D dev team here at Microsoft. Thanks a lot.